Alright, this last video for Unit 12, Gas Laws, is about the kinetic molecular theory, Graham's law, and then how real gases differ from ideal gases. So let me just go through the kinetic molecular theory a little bit. We're on page 7, kind of in the middle of the page. So I'm not going to read all of these things to you because you can read, but I'm just going to highlight a few important things. So all of the gas laws we've talked about are based on these assumptions, all right? Some of these assumptions, part of the KMT or kinetic molecular theory, are true assumptions, like that that is the case for real gases. Some of them only apply for ideal gases, all right? So the first point, yeah, that's true. They're really tiny particles. Those gas molecules are really tiny particles, and they're in continuous random motion. We also know that the distance between them is very large compared to the size of those molecules. Those molecules are teeny, 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 tiny. So the space between them is ginormous compared to it. Gases, we assume that they have no attraction for one another. This is an assumption that we make for ideal gases, all right? Real gases actually do experience attractive forces, which I will touch on at the end of this video. We also assume that gas molecules move in straight lines in all directions, and they collide frequently with one another and the walls of the container. That's actually true. That's what is pressure, all right? That's how we measure the pressure of a gas. We also assume that no energy is lost by the collision of those gas molecules. And that is an assumption that, again, only works for ideal gases. That really there is some energy lost when those particles collide. Really, those collisions are not actually perfectly elastic. They do lose some of their energy over time, okay, as they're being like transferred. All right, and then the last one on here says the average kinetic energy for molecules is the same for all gases at the same temperature. That is true. Like, that is a true statement. Not making an assumption here. All right, and that is what we see in just a little bit. All right. So just an FYI, gases are most ideal at high temperatures and low pressures, okay? And the reason why has to do with making it more ideal. So remember, particles, actually we're gonna, let me back up. We're gonna answer this question at the end of the video, all right, when we talk about real versus ideal gases. So number 6, that last one we were talking about, that average kinetic energy, that's what's going on here, all right? There's actually supposed to be more of a space in between. Yours has it. It's actually divided right here. All right, so kinetic energy, the average kinetic energy is equal to 3/2 times RT. You're never actually going to solve this formula, but just know that it exists. We could also say that 1/2 mv squared is equal to 3/2 RT. 1/2 mv squared is the kinetic energy. That's a physics formula. That V is velocity, hence why it's a lowercase. If it's a capital V, it stands for volume. All right. So we can actually do some manipulation. So if you end up solving for the root mean square velocity, which is URMS, the root mean square, meaning like you take the square root of this formula. You're actually missing the square root sign on your packet. I do apologize for that. So make sure you fill that in. So this is a formula that we're going to use. All right. This URMS equals square root of 3RT over mm, where R is going to be the energy R, T would be the temperature, whatever this gas sample is at, and mm is molar mass. Now, molar mass has to be in kilograms per mole, and that has to do with the way that the physics units work out. But yeah, just make sure you have molar mass in kilograms per mole. All right, so let's go through some, one more thing, and then we'll get into some practice problems. So this URMS equation is for finding the speed of one gas sample, like of a gas sample. We could also look at this formula and compare speeds or velocities of different gas samples, comparing them to each other. So through the power of combining the formulas and all that stuff, you end up getting to this formula. R1 or R1 over R2, the rate of gas 1 over the rate of gas 2, is going to be equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Now, technically, these molar masses should be in kilograms per mole, but you can leave them in grams per mole because you're looking at a ratio. And this is Graham's law. Comparing gases. I think technically both are considered Graham's law, but this, when I hear Graham's law, this is the formula I think of. So you can leave it in you can leave this in grams per mole, but when you're looking at the velocity of a single gas sample, you will need to have it in kilograms per mole because you're not comparing it to anything. So for example, number 14, we're going to calculate the average velocity of a sample of helium atoms at 25 degrees Celsius. So this is going to be that URMS equation, and that's going to be equal to the square root of 3RT over MM. All right, now URMS is going to be meters per second. All right, we meters per second. Now, I use velocity and speed as, I use them interchangeably because in chemistry, we don't care about the direction the gas sample's moving in. In physics, velocity has either a positive or negative depending upon the direction it's moving in. That doesn't apply here, okay? So they're interchangeable in my mind. Helium on the periodic table has a molar mass of 4.00 grams per mole. We're going to need that in kilograms per mole. So you're going to divide it by 1,000, and you'd have 0.00400 kilograms per mole. All right, so we're just going to plug this in. R is at 8.31 joules per Kelvin mole. And T is going to have to be in Kelvin, as always, when we are dealing with gases. We don't want to end up taking the square root of a negative number. That might make it a little bit challenging. Divided by the molar mass in kilograms per mole. I just realized that I have the wrong number written down for the temperature. For some reason on my paper I have 288, and I'm just going to recalculate to make sure that I didn't use the wrong one. 298 divided by 0.004, square root it. Okay, so I have the right answer. I don't know, I wrote it down wrong. All right, so you should get 1,360 meters per second. Okay, and if you leave it as grams per mole, you're technically solving for millimeters per second, which is just a weird unit. So make sure you convert that. Oh, wait, I think you'd be solving for, I don't know. Make sure it's in kilograms per mole. Just make sure your molar mass is in kilograms per mole for this formula, okay? So, some things to look at. As you can see, the molar mass of the gas is on the bottom. So as we increase the molar mass of the gas, we're going to end up solving for a smaller number because you're going to be dividing by a larger number and then taking the square root of that. So your speed is going to decrease as the gas increases in molar mass. So that's an important thing to keep in mind. And that's what we're going to look at when it comes with the next problem, comparing two gas samples. They're going to be moving at different speeds. All right, so for example, oxygen, O2, diffuses at a rate that is 2.23 times faster than a sample of a reddish-brown gas. We don't know what that gas is. We're going to determine the molar mass of the unknown gas. So some things that we have. The rate of oxygen is 2.23 times faster than the rate of the unknown gas, where the unknown gas is X, right? Oxygen is 2.23 times the other one's rate. So oxygen is moving faster, since it's going at 2.23 times what the other one is moving at. So since oxygen is moving faster, the molar mass of oxygen, which we can leave that in grams per mole, is 32 grams per mole. That should be less than the molar mass of sample X, of gas X. Should be less than that. Or 32 should be less than that. Sample or gas X should weigh more, should have more of a molar mass than oxygen, since oxygen is moving faster. All right? So we can set up this formula. So it doesn't actually matter which one you put on top or on bottom. I'm just going to put oxygen on the top. So the rate of oxygen gas over the rate of gas X is going to be equal to the square root. And it's always like, so whatever you have as your rate in the square root, it's going to be flipped. So it'd be molar mass of gas X over molar mass of O2. All right, and that's just from the formula. All right, so since that is there, hold on, I'm checking to see if this is on your formula sheet. I don't believe this one is. No, this one is not on your formula sheet. So I definitely, this is one of the few that I suggest you memorize. Neither of the Graham's Law formulas are on the formula sheet. All right, so now let's fill in. Well, we don't know the actual rates of oxygen or of gas X. We don't know them, but we know enough information that we can plug in some numbers. So I'm going to set I'm going to set the rate of X to be 1 meter per second. And I know that oxygen is working at, or moving at 2.23 times whatever gas X is moving at. So therefore, oxygen would be 2.23, the rate of oxygen. It doesn't matter what numbers you use here as long as this top number is 2.23 times larger than this bottom number. And then that equals the square root of molar mass of X, that's what we're solving for, over 32. And you can leave that as grams per mole because, again, you're doing a comparison. The units end up canceling out. All right, so solve that. You should get the molar mass of the unknown gas to be 159 grams per mole. Okay, which is greater than 32, which means it's moving slower because we know that oxygen is moving at 2.23 times faster than this unknown gas. All right, just a few more things. Let's look at the next problem. We're going to consider 3 identical flasks that are filled with different gases. We're told that flask A contains carbon monoxide at 760 torr and 0 degrees Celsius. Flask B contains nitrogen gas at 250 torr and 0 degrees Celsius. And flask C has hydrogen gas at 100 torr and 0 degrees Celsius. So we have 2 questions here. In which flask will the molecules have the greatest kinetic energy and why? I added in the why. Please make sure you include that in your paper. And in which flask will the molecules have the greatest root mean square velocity and why? This is a great AP problem. So just FYI, great AP problem. Can I move this up without? Oh no. Oh, I just messed it up. That was weird. Okay, I fixed it. All right. So let's tackle A first. So we want to know which one's going to have the greatest kinetic energy. Well, let me look back at this page right here. This section right here gives us the answer to that question. Any gas will have the same kinetic energy if it's at the same temperature. The molecules are just going to be moving at different speeds. Notice, kinetic energy is the only thing that goes into kinetic energy for a gas is the temperature of the gas. I mean, yes, it's mass and velocity do play a role, but since this formula right here, the only thing that applies is temperature. Right? So, looking at the three flasks, which one's at the greatest temperature? Because that's going to be the one with the greatest kinetic energy. Oh, they're all at the same temperature, you say? Therefore, they would all have the same temperature. Or sorry, all have the same kinetic energy. Because kinetic energy is equal to 3 halves, oops, that's supposed to be 3 halves RT. And so since all are at same temperature, all have same kinetic energy. Okay. The velocity and the mass do play a role in kinetic energy, but because they're both playing a role, we know that as mass increases, velocity decreases. So if they're all at the same kinetic energy, what's going to be different there is going to be the mass and the velocity. All right, so for B, kind of already hinted at this, in which flask will the molecules have the greatest root mean square velocity? So that's that URMS equation. Square root of 3RT over mm. Right? So what we need to worry about here, well, they're all at the same temperature, and R is a constant, and 3 is a constant as well. So the only thing that's going to apply is the molar mass. That's going to influence the velocity. All right? So the one with the largest velocity will be the one with the smallest molar mass. All right? So if we look at the three gases, the one with the smallest molar mass is hydrogen, so therefore flask C. Because hydrogen is the smallest. All right, one last little bit, and this is how real gases differ from ideal gases. All right, so looking here, a lot of stuff on this page, but you have it all on yours as well. So we're mainly going to be talking about the second and third. Is that right? I feel like my numbers are off here. Hold on. Yeah, I mean, we're going to be mainly talking about the second and third. And the part of the second that we're going to be talking about, let me go back to this. Oops, too far. The part of the second postulate that we're talking about, the first sentence is true. That works for real and ideal gases, that there's a lot of space between the gas particles. The part I forgot to mention is this one, the second sentence, that the volume occupied by the individual gas particles is mostly, we consider it to be negligible. That is not true. We know that gases actually take up space, right? So that's the part of postulate 2 that where real gases deviate from ideal. So looking here, so in the second, this talks about the second postulate, and this one talks about the third postulate. All right. So gases are a type of matter matter, the definition of matter is that it has to have mass and take up space. Therefore, those individual gas particles do have a tiny, tiny volume. It's just not it's not zero as assumed by the second postulate. So those particles do actually take up a little bit of space. And then those gas particles actually do experience attractive forces between them. In order for you to recondense or to condense a gas, there has to be some forces holding those gas particles together. If there were no forces holding them together, then you'd never be able to recondense a gas. And we know we can do that. So this is why they deviate from ideal gas behavior at high pressure and low temperature, because the higher we like gases to have they are more ideal at low pressure and high temperature, which is what we were saying before. The higher the temperature, the faster they're going to be moving. Therefore, there won't be as much time for them to experience interactive or attractive forces. So the lower the temperature, the more those intermolecular forces actually play a role. Pressure comes into play with, and volume as well. The higher the pressure, the closer those particles are together, and therefore the more those individual particles their volume is going to be influential. When it's low pressure, those particles are really far apart. Therefore, you can consider them to be negligible volume for the individual particles. Okay, so to correct for non-ideal behavior, when a gas is deviating from ideal gas behavior, we can correct for it using the ideal gas law, and you add and subtract correction factors to the pressure and volume, and that's what the van der Waals equation is there. You're never actually going to solve this formula. It's more of discussing why one gas would be more ideal than another. Right, as we're going to see in number 17. Okay, so I'm going to kind of work through this van der Waals equation in number 17. And you have a lot more space than I do, and on my actual handout, I took up more space than the box provided. So write small or grab another sheet of paper. Okay, so in number 17, we're going to explain in terms of the van der Waals equation why hydrogen chloride, HCl, is much less ideal than hydrogen gas, H2. All right, so we're going to talk about two things. We're going to talk about volume and pressure. So in terms of volume, if you look at that van der Waals equation, we have a factor being subtracted from the volume. Okay, so we're going to talk about why we're having to subtract that factor. So the HCl molecule itself is larger than the H2 molecule. All right. So therefore, the HCl takes up more space in the container. The individual particles of HCl are going to take up more space. I'm going to write that down. So they take up more container space. That's why we have to subtract a correction factor. I don't know what that bell was for, or what that thing was. It is nowhere near the end of school right now. I lost my train of thought. So a correction, and drop my pen. Oh, fun. So correction factor is subtracted. Subtracted to bring the volume back to more ideal. Okay. Now, in terms of the pressure, HCl is a polar molecule. So therefore, it experiences dipole-dipole forces. And H2 is nonpolar. So it experiences London dispersion forces only. So since the intermolecular forces that HCl experiences are stronger than the ones hydrogen experiences, they play more of a role, and therefore the particles are going to be closer together and they're going to be exerting less pressure on the container walls. Therefore, we have to add a correction factor to the pressure to bring it back up to ideal. I'll write that down. So since HCl experiences stronger intermolecular forces than H2, the pressure of HCl is lower because the particles, that's a weird E, I swear it's there, are interacting with each other. So less collisions. So a correction factor is added. All right, so since HCl is a larger molecule and polar, that's what makes it less ideal than hydrogen gas. So the most ideal gases are going to be small, non-polar gases at high temperature and low pressure. Okay, I'll write that down here. It's not really part of this problem. It's related. So yeah, the most ideal gas is going to be one that is small, and that is nonpolar, and conditions of high temperature and low pressure. Okay, so that is it for Unit 12. All right, that's it for the other than the last little unit we're going to do of this year. That's it. I've taught you everything for the AP exam.